This video is about gradients and intercepts of graphs. A graph has a y-axis and an x-axis. As physicists, we try to choose what we plot on the y and x-axis so that the data produces a straight line. Two important features of a straight line graph are the intercept and the gradient. The y-intercept is where the line crosses the y-axis when x equals 0. If the graph is drawn with a false origin, you have to be extra careful to make sure that your y-intercept is not just read off the graph. X equals 0 when y equals the y-intercept. The gradient of the graph is sometimes called the slope. It is sometimes simplified as rise over run. When calculating a gradient, you start by choosing 2 points on the line, but these do not correspond to 2 points of the data that has been plotted. And in fact, in exams, it's always a good idea to make sure the 2 points on the line you choose are not too close to the data points so that the examiner can clearly see that you've used the line and not the data points in the gradient calculation. Here I've chosen points which I've marked with a green spot at the top and the bottom so that they are on grid lines for the x-axis. That will make it easier for me to read values off the x-axis. The two places that you choose on the line should be as far apart as reasonably possible. We sometimes refer to using a triangle when calculating the gradient, but I think this can cause some problems. When you first meet gradient, you might learn about counting squares and dividing the number of squares in the y-axis by the number of squares on the x-axis. But actually the number of squares isn't very important because it depends on what the scale is on the x and y axes. So when you first learn about gradients, you may learn that the difference in the y-axis divided by the difference in the x-axis is the gradient. And this is true, but you shouldn't be counting squares. What you should be doing is reading the maximum value and the minimum value of the scale on the y-axis and the same on the x-axis. So a better triangle might look like this. And it doesn't look much like a triangle. And then we can mark off the values of the y-axis and x-axis that we're going to use in our gradient calculation. The first data point is at position x1, y1, and the second data point is at position x2, y2. And these values would be read off the scale on the x and y axes. The gradient calculation, now the difference in the y-axis is the final value of the y minus the initial value of the y. And it's the same with the difference in the x-axis. There are advantages to doing this. For example, if there is some multiplier on the axes, then that is incorporated into the gradient calculation. Now in physics we tend not to work with abstract numbers, but numbers that actually represent something physical. And so the gradient represents some physical quantity on the y-axis divided by some physical quantity on the x-axis. By way of a very simple example, imagine that we plotted a distance on the y-axis and a time on the x-axis as a body is moving. The gradient would therefore represent a distance divided by a time, which we know as a speed. And if the distance is measured in centimetres and the time in seconds, then the gradient would be in units of centimetres divided by seconds, or centimetres per second. And that would be the unit of the gradient, and therefore the unit of the speed that the gradient represents. In the Isaac Physics sheet A5, you are presented with some graphs and asked for the physical quantity corresponding to the gradient and the y-intercept. So that would include the numerical part of the physical quantity, its unit, and also what that quantity is. Is it a speed? Is it a displacement? Is it a velocity, a force, and so on. Now if you have the situation where we do not have an easily identifiable y-intercept because there is a false origin and so it is not 0 at the origin of the graph, then you will need to use the equation for a straight line to calculate the y-intercept. The equation for a straight line is y equals mx plus c. Y is whatever quantity is plotted on the y-axis. M is the gradient. X is whatever quantity is plotted on the x-axis, and c is the y-intercept. Many equations in physics are already in the form y equals mx plus c, but with c, the y-intercept, as 0. And here's just a few of them I've written here. Some equations, such as this one for internal resistance, is in the form y equals mx plus c, but just needs a little bit of manipulation to get it in that familiar order of variable equals constant times variable plus constant. And some equations can be made to be in that format with a little bit of careful plotting. For example, in this equation, if v squared is plotted on the y-axis and s is plotted on the x-axis, then the gradient would be 2a and the y-intercept would be u. This is in the form y equals mx plus c if it's rewritten like this, where the v squared on the y-axis, s on the x-axis, and the 2a is the gradient, and the u squared is the y-intercept. So even if a relationship does not look like it is a straight line, the data can usually be manipulated to make the results produce a straight line graph, so that we can extract from that graph the gradient and the y-intercept, values that are very useful.